Okay, so here is class 4 of Elements of Mechanical Design, ME370. I'm going to make a series of videos. I'm wearing my Don't Panic shirt. That's a reference to Hitchhiker's Guide to the Galaxy. Try it out. Anyway, we're going to introduce pressure vessels today, and we're going to take a look at the different pressure vessels. There's different types of stresses that are in pressure vessels, so extra types of stresses we haven't covered in classes 2 and 3, which are the review. And maybe you've had pressure vessels in mechanics and materials, but if not, well, we're going to introduce them today. We're also, one of the main important topics within pressure vessels is that there's easier equations to use that we can use when pressure vessels have thin walls, right? So we call them the thin wall approximation. And then we're going to introduce 3D Moore circle as well, and you'll see why that's relevant to the pressure vessels. So you think of pressure vessels. I was a marine engineer for my undergraduate, so I spent a lot of time on steamships, and we had boilers, and that's a big time pressure vessel. Very important. And you got water and steam inside this, and you got fire inside here, passes the burning whatever you have, usually oil on a ship, or it could be coal, what have you. The gases pass by a bunch of tubes. And with those water and steam inside those tubes, it produces steam, right? That you could drive the turbines, make the ship go putt through the water. And as part of that steam plant, there's lots of these heat exchangers for various types of heat exchangers. The boiler's a heat exchanger itself too, but there's other kinds of heat exchangers along the way, and those are under pressure. So they're pressure vessels. You might have heat exchangers also in a refrigeration system. Those are all heat exchangers. And all kinds of different things. Heat exchangers, right? Heat exchanger. But they're under pressure. And then all the pipes that connect them, those are considered pressure vessels. Or it might have other things like a freestanding tank. It's a pressure vessel. And there's a real good reason we might want to cover this, because in the history of engineering, one of the things that was going on as the Industrial Revolution started to expand, people wanted to increase the amount of power they were getting out of the steam turbines, so they made the boilers higher and higher pressure. Well, all those boilers start to explode, kaboom, because there wasn't any kind of like standards to say, okay, this is how you do it. It's like everybody was calculating their own thing. And, it wasn't like they weren't able to calculate. There was no standard way of doing things. So that's actually the reason why the American Society of Mechanical Engineers actually came about, after boiler explosions. Well, pressure vessels are very much tied to us as engineers, and, standards and codes and all those types of things, really had their start with, exploding boilers. And, so historically, this is an important thing that we would want to know about. So we're in section 314 of Shigley, which in at least one of the versions is page 127. Well, you get kind of an idea where it is. I think I've assigned anomaly assigned the 11th edition, but this might be the page number from the 9th edition or 10th edition. So in a standard pressure vessel, right? So we would just have a generic thing. We have first off, the main equations that we're going to see, I'm just presenting them right here. I'm not going to derive them. I'm going to derive the thin-walled versions of them. But you'll see here, we have 3 different equations. We have a T, an R, and an L. And let's try to think about what those are right here. Okay, the T is going to be tangential. That's going to be probably the hardest one for you to think of. So let's put that on the back burner. We have R, that's radial. Now it just kind of makes sense that if you have a pressure vessel that's a contained thing, and here we see the cross section of a pipe, we see that we have pressure on the inside, PI, right? And that pressure is trying to get out, push outwards. So the radial stress that you would experience is going to be the compression that these walls are feeling as they're getting crushed. They're getting put, one of them's stationary and the other's trying to get pushed out. Well, kind of quasi-stationary. You can imagine though it's getting squished. That's the radial stress of its squishiness. And right here on this diagram, you could see that it gets diminishingly smaller and gets to be 0 on the outside edge, because obviously the outside of the pipe or whatever the tube or whatever has the pressure on the inside of it, the outside is going to be atmospheric pressure, which we'll just assume that everything is 0 at atmospheric pressure. So we call that gauge pressure, by the way. So if you see something that's pounds per square inch PSI G, what they really mean is that they're not, the scale is based off atmospheric pressure being 0, and so we assume that anything that's below 0 is going to be a vacuum, right? So anyway, so it's going to be, it makes sense that it's on the outside of this in the radial direction. There's nobody on the outside of the pipe to push except for atmospheric pressure. Let's just say that that's our reference as 0 right there, right? So it's 0 on the outside. So it's maximum here, and its compression, you notice they show that it's negative, right? And again, but it gets less and less of having any pressure until any stress until it gets to 0. So, and if you were to put these values in, you'll see that we're using RI, RO, and if you look closely, one of the R's doesn't have a subscript. That's the actual radial position from the center of the thing. So this equation is really giving you the distribution of the stress, and it's really starting from RI, right? It doesn't make any sense for anything less than RI, right? So starting at RI, this equation is showing that curve of a distribution. Does that make sense? Hopefully. Okay. Now, if you set the R, the only one that's a variable in this equation, that guy down here in the denominator, if you set him equal to RO, what you end up finding is that you get 1, right? And so you have 1 minus 1, so that thing, it just goes away. It's just 0. And if you set, there's a little bit of algebra here, if you set R equal to Ri, what you end up finding is all of this stuff just works out, and you end up just having negative Pi, right? So the compressive is negative because it's compressive stress. That's what this equation is describing, is the stress state at any position really between Ri and Ro. And it's going to, right here on the inside surface, it's going to be equal to negative times the pressure. And it just kind of makes sense that the compression right there on the inside wall of the pipe, the stress is going to be equal to what the pressure is on inside, right? Make sure we're thinking about those little stress elements and the stress, and right on the edge on that for inside stress element, it's going to be equal there. So that's maybe one of the first equations we could pick apart. The next one is very similar. Notice how similar these equations are to each other. This is the longitudinal stress. All right. So this supposes that this, and maybe I ought to draw these things out right here. So let me switch over to my document camera, which is a little easier to draw because I'm kind of tired of my tablet. It's kind of makes me unhappy. All right. So here's your document camera, and so I could draw some of these things out here, and I didn't have the equations written down on my notes here. But if you can imagine for the longitudinal, right? So see, and I write long this way right there. I write that it's the longitudinal right there. Imagine now this thing right here is a tube, right, that we're looking at, and it has a cap to the end of it, right? So on the inside, so it's just, there's a blank on the end, right? So there's pressure going everywhere, pressure everywhere inside this, and there's also pressure on the end cap right here. Now, remember when we're looking at stresses, we're looking on the inside of the piece. So this thing is continuous, like in that direction, right? As we're going in that direction, but we're just looking at a cross section of the thing that's been cut away because we had to cut it to look inside it and see the stresses. Well, in the longitudinal direction, which is that direction right there, there's going to be stress, right? The stress distributed all along that face because over here on this side, there's pressure pushing on that end cap. So in order for this thing to stay in equilibrium and not go flying off into space, it has to have some stress. That's the longitudinal stress, right? And that longitudinal stress, I'll write it down here, is going to be internal pressure times the inside radius squared divided by the outside radius squared minus the inside radius squared, right there, right? And notice there's no R. There's no R without a subscript. That's because it's uniform all the way across there. It doesn't vary with R. You'll notice that there is no distribution symbol there for your longitudinal stress. Now the last one, the very last one that we have to worry about is this tangential. And it's probably one of the most important of the stresses right here. We give a little subscript T. But another name for it you'll hear is hoop. Hoop stress. What does that mean? And even if you look at this, and this is symbolizing the sigma T right there. This is the distribution of that hoop stress within a cylinder wall. So how could you think about this? Well, I think this word hoop is really the key to understanding what that might look like, right? Now, picture yourself inside of a very large hula hoop. So this is you, right? And you're happy, so you're smiling. And you are, let's see, we'll give you a t-shirt. And you are standing and you're pushing with your arms inside that hula hoop. We'll give you some shorts because it's still summer, right? And you have little squatty legs, right? So let's say that you're pushing this thing out. So you're pushing outwards. You are the thing that's causing pressure. How is that hula hoop going to break? If you kept pushing, how is it going to break? Isn't it going to snap right there? What you've done is you've created hoop stress, right? Hoop stress is a stress in the hoop that's coming in that direction right there, right? If we split the thing apart, you're creating tension into this thing. If we broke the thing apart, there'd be tension here and tension there that of the thing trying to come apart. So I associate the word hoop with being inside that big hula hoop and trying to push that thing out. That's the hoop stress. And it's tangential, right? It's tangential surface. So it really is coming in this direction right here. So this is, and so the equation for the hoop stress, let me get this right. I think I swapped the P and the R, but that didn't matter right there. You'll see it's almost identical to the radial and the longitudinal in this first part over here. So we have the RO minus RI. Oh, that's got to be squared. Both of them have to be squared. Make sure you don't put the square on the outside there. There you go. And then this part right here is what's different. You have 1 plus RO squared divided by R squared. And you'll notice that R does not have a subscript. All the other ones do. These are all constants. This is the one that varies with radial position as measured from the center of the thing. So as you're coming on here, and of course it doesn't matter anywhere until you start getting to the RI, right? This equation doesn't apply to anything. It starts applying right there at RI. And interestingly enough, it gets it's largest on the inside, but then it starts to diminish. But there still is stress here. Now, almost always you're going to find that the tangential is going to be larger than the other two stresses. In fact, right here at this outside fiber, when R is equal to RO, look what happens right here. We have RO squared over RO squared. This whole thing becomes 2. So tangential here on the outside fiber is 2 times the longitudinal, right? So that's the same equation as that right there. So here's things that we were just observing. So the concept here is that if we took a small little cube that's right there on the inside surface of this pressure vessel, it would feel normal stresses in 3 directions, right? So I'm going to draw it with a little bit of a slant to it right here. Whoop. Let me make that a little bit more like a square. All right, so I'll make sure I draw this nice cube right here. So this cube aligned with this right here, it would feel, this would be R, and it would be compression. It's always compression, unless it was like maybe under a vacuum. Maybe if inside here was a vacuum. Or, by the way, I'm only writing the equations for when we have internal pressure. We could have external pressure. I don't know why I just said external. External pressure, as in, say, a submarine, right? That's a pressure vessel, but the pressure is the water on the outside pushing in, right? So we could have, these things could actually be arranged differently. I only did it for internal pressure vessels. So in this case, we have compression on the inside, on the radial side, on the radial face. That guy right there is that face right there. We also have longitudinal, so it's coming out of the page here, and that's going to be that way right there, and I'll write that. And then we're going to have tangential right there, and I'll put a little T next to that. So we have tangential, radial, and longitudinal. And all of those stresses are present within a pressure vessel. Notably, the radial only really matters, and most of the time we're always looking at surfaces of things, so it's only on the inside surface of the pressure vessel where the radial actually matters and will be anything. Most of the time, a lot of times, we'll be looking on the outside surface. Unless told otherwise, we're probably looking on the outside surface, and radial is 0. I find that students get obsessed with the radial only in special circumstances when we're on the inside surface of a pressure vessel. Are we ever going to consider the radial stress? So I think that's long enough for this video, and I'm going to go to thin-walled pressure vessels in the next one. So let's end the video. It's already long enough. 17 minutes, long enough. Goodbye.